In this video, I'm going to go back and talk about 7.6, which is going to talk about moments, centers of mass, and centroids. Just going to talk about this before we go on to chapter 8 because it's one of the main applications of integration that we're going to talk about in Calculus 2. So our objectives here are to find the center of mass of a one-dimensional system, to find the center of mass in a two-dimensional system, and to find the center of mass of a planar lamina. I've gone ahead because the work is pretty time consuming here and I've worked out all my examples. We're going to go through and we're going to talk about some definitions and our units of measure here in our first objective, and then we're going to go on and go straight to some examples as we get to the definitions for the next objective. So the mass is a measure of a body's resistance to motion and is not the same thing as its weight, though they are related. Remember that weight is a force. Force is equal to mass times acceleration. And weight is specifically the force that is from the acceleration due to gravity here. So weight is equal to mg. It's going to be an important formula for you in physics and engineering. So our units of mass that we're going to talk about in the US system will be slugs. Slugs are related to pounds by this equation here, that a pound is equal to a slug times a foot per second squared. In the international system, our units of mass will be kilograms. And remember, our unit of force was a Newton, and a Newton is a kilogram meter per second squared. Meters per second squared is our unit of acceleration in the international system. In the CGS system, the centimeter gram second system, the gram is the unit of mass. Our unit of force is the dyne, and a dyne is a gram centimeter per second squared. Our conversion factors are here. I think we talked about those previously. I'll leave them right there while I keep talking about this next idea right here so that you have those conversion factors and you can write them down. So now that we know what mass is, we can talk about the idea of center of mass, which is a particular kind of moment that we're going to talk about here in Calculus 2. Moments are going to be very important in physics and engineering and even in calculus. And we'll have additional types of moments that we're going to talk about later. So moments of mass here, moments of inertia, all types of moments that we can have. We find a moment about a point, or we can have a moment about a line. So we'll start by talking about moments about a point because it's easier to do. And I'm going to use a seesaw as an example of that, a balance with a fulcrum. And then we'll get to where we have moments about a line, and we'll use those to find centroids and center of mass of planar lamina. So let's start off with what a moment is. A moment is equal to the mass times the length of the moment arm, where the moment arm is how far away that mass is placed from the fulcrum. In this case, the center of mass, or whatever, how far of a distance away that is. So a child, in example 1 here, a child of mass 20 kilograms sits 2 meters to the left of the fulcrum here at point P. And another child of mass 30 kilograms sits to the right of the fulcrum. Get rid of the answer here so we can solve for it. So it's to the right of the fulcrum so that the seesaw will balance. I already know that that the 30 kilogram child needs to be sitting closer. So I kind of drew it that way in the picture. We know if they both sit the same distance away that the seesaw the teeter-totter is going to rotate that way towards the child that has more mass if they sit the same distance away. So the child with more mass is going to have to sit closer to the fulcrum, or the child with less mass is going to have to sit further away from the fulcrum. So let's go ahead here and see how this is going to work. So our left moment, which is the lighter child here, the one with less mass, is going to be 20 kilograms times 2 meters, gives me a left moment of 40 kilogram meters. The right moment is going to be 30 kilograms times x that we don't know. And I'm going to call that x2 because this was m1 x1, and this is going to be m2 x2. So they need to be equal to each other for me to have the seesaw in balance. So I'm going to set them equal to each other. 30 kilograms times x2 is equal to 40 kilogram meters. Divide both sides by 30 kilograms. And I get x2 is equal to 4/3 of a meter. And 4/3 of a meter is an exact answer. We know that that's a repeating decimal, so I'm going to approximate that as 1.33 meters, but it's exactly 1 1/3 meters. It's another way to say that. So it's exactly 1 1/3 meters. And I tried to draw it that way here, where this child sat 1 1/3 meters away from that fulcrum. So that's one type of problem that you're going to get in a one-dimensional system, where you are finding a moment around a single point, a fulcrum like that. Now, if we have a two-dimensional system, we can have a center of mass in a two-dimensional system where we know the ordered pairs for all of the weights and that they're centered at individual points there. So the moment about the y-axis for such a system will be m sub y equals m1 x1 plus m2 x2 plus dot 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 plus mn xn. And the moment about the x-axis is going to be m sub x is going to be m1 y1 plus m2 y2 plus dot 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 plus mn yn. So then our center of mass, x bar, that's going to be our average x value. Y bar, that's going to be our average y value, which will be the center of mass or the center of gravity, is x bar is my over m, and y bar is mx over m. This center of mass or center of gravity is called a centroid. It's kind of the center of this object, where I could put my pencil or my finger or something like that and balance everything on the tip of a pen or on the tip of a pencil or on the tip of my finger, because that's where all of the mass would be centered. At that point, if we moved everything to a single point like that, and it would basically be the same as the system that has the weights distributed all around in these ordered pairs. I think I said that the total mass of the system M is M1 plus M2 plus dot 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 plus Mn, and we're going to need that as we find X bar and Y bar. So let's look at example 2 here, where I have a mass of 12, let's say, grams, 6 grams, 4.5 grams, 15 grams, whatever my unit is here. And it's located at, we have a coordinate system here. So mass 1 is located at 2, 3 up here in quadrant 1. So 2, 3, mass 1 is up here. And then mass 2 is at -115. So mass 2 is somewhere up here. Mass 3 is at 6, 8. So it's way up here. And then mass 4 is at 2, -2. So it's down here. And they're different masses, so they're going to be pulling more or less based off of how much mass they have. And I just want to see if I wanted to put all those masses together as a single mass, kind of where would that center of mass be? So the total mass of the system is 12 plus 6 plus 4.5 plus 15 is 37.5, or 75/2. My m sub y is going to be my m's times my x's all added together. And that gives me 75. My m sub x is going to be my m's times my y's all added together. And that's going to give me 132. I'll give you a second to look at that and come up with those numbers yourself. 12 times 2 is 24. 6 times -1 is -6. 6 times 4 is 24, plus another 3 is 27. Don't need the 0.0. And then 2 times 15 is 30. And then add all those together. 22 plus 27 is 49. Let's see, sorry, 18 plus 27 is 45, plus 30 is 75. That's right. So 18 plus 57 going to be 75 there. That's right. And then 12 times 3 is 36. 6 times 15 is 90. 8 times 4.5, that's 32, plus 4 is 36. And then -30 there. So that's 126 plus 6 is going to be 132. And then we have our my was 75 divided by 75 halves is going to give us exactly 2. And our 132 divided by 75 halves, that's not going to be a nice answer. 264 over 75 is 3.52. So this fraction doesn't reduce. This is my exact, but this is also exact. Comes out exactly to be this. So there's no rounding here. Just depends whether you want to give a fractional form or decimal form like that. But this 3 and 52/100ths is exactly the same thing. So now we move on to the major application of this section is the center of mass of a planar lamina. And we're going to get this idea of using area between curves and so on, like we have done from chapter 7 so far. So far in this section, we've assumed that the total mass of the system was distributed at discrete points in a plane or on a line. We're now going to consider a thin, flat plate of material. Think like a piece of paper, a sheet of cardboard, aluminum foil, something like that, that's thin and flat like that, that's of constant density, and that's going to be called a planar lamina. So typically units of density for planar lamina are in units of mass per units of area. So something like grams per cubic meter or something like that. per square meter. Grams per square meter, something like that. So I know we normally think of density as mass per unit volume, like grams per cubic centimeter in physics. And we use the variable rho for both of those. But since we're dealing with an area problem here, it's going to be mass per unit of area. Not that we can't have density functions in calculus that are mass per unit volume, just not in these problems that we're doing right here in two-dimensional calculus. We'd have to save those for three-dimensional calculus. So density will be denoted by rho, the lowercase Greek letter rho, which stands for density in physics. So to find moments and center of mass of a planar lamina, we're going to need these equations. Write them down somewhere. These are going to be important. You'll need them for reference. That my moment about the x-axis, m sub x, is going to be rho times the integral from a to b of the average of the y values times the difference in the y values, dx, of these two functions that we're going to have for our upper bound and our lower bound. F of x will be our upper function and g of x will be our lower function. Moment about the y-axis is going to be m sub y is going to be rho integral from a to b x times f of x minus g of x dx. And our center of mass, x bar, y bar, will be x bar is equal to m sub y over m, and y bar will be m sub x over m. So the mass of the center of mass of the planar lamina is going to require us to find the total mass of the lamina, m. And before we could just add all the masses together because we had them all listed in the table. We can't do that anymore. We're going to have to integrate to find the total mass. So m is going to be equal to rho times the integral from a to b of the difference between f and g dx. So let's go ahead, and I think this is example 3. Let me make sure. It's either example 3 or 4. Yeah, it's 3. This is going to be my last example here. This is example 3. So let's find the center of mass of the planar lamina of uniform density rho bounded by the graphs of f of x equals 4 minus x squared and the x-axis, which is going to be g of x equals 0. And I've drawn a little picture of that this is -2, 0, and this is 2, 0 over here. And this is 0, 4 up here at that vertex. And the shaded area there represents the region in which I'm interested in finding the center of mass of. So m, my total mass, is going to be rho times the integral from -2 to 2 of 4 minus x squared minus 0, which doesn't do anything. So 4 minus x squared dx is going to be 4x minus x cubed over 3 from -2 to 2. So that's going to be 8 minus 8 thirds plus another 8 minus 8 thirds is 16 minus 16 thirds. Comes out to be 32 thirds times rho, as the constant multiplier is 32 rho over 3. So hang on to that. That one's going to be an important number to hang on to right there. And then m sub x is going to be the average of the y values times the difference in the y values. So average of the y values when I add 0 and divide by 2 here. That's still 4 minus x squared over 2. Difference in the x values is 4 minus x squared. And we have a multiplier of rho. We're going to integrate from -2 to 2. This is dx. And then I'm going to take this multiplier of 1/2 that's divided by 2 out front and make that rho over 2. I have 4 minus x squared, and another 4 minus x squared is 4 minus x squared squared. I'm going to expand that into 16 minus 8x squared plus x to the 4th dx. I've still got rho over 2 on the outside. That's going to make this 16x minus 8x cubed over 3 plus x to the 5th over 5, evaluated from -2 to 2, the multiplier of rho over 2 out front, rho over 2 times, and this is going to be 32 minus 64 thirds plus 32 fifths, and I get all that again. So this is really 2 of these is going to make the divided by 2 go away. So because this is because it's odd, I'm going to get 2 of these things right here. And so this is going to be rho times 32 times 15 minus 64 times 5 plus 32 times 3 over 15. And that all becomes 256 rho over 15. I'm just going to cut out some steps here. So this is 256 rho over 15. If you use your calculator, you'll be able to simplify that there. So there's another piece to the puzzle that we need. So that was mx equals 256 rho over 15. That's one of our important things. Now we move on to finding m sub y. And m sub y is going to be rho times the integral from -2 to 2 of x times 4 minus x squared dx. So we go ahead and distribute that x there. That's 4x minus x cubed here. So that makes 4x squared over 2 is 2x squared. And this is going to be minus x to the 4th over 4. Plug in your 2 and your -2. This is 8 minus 4. And that's going to be another 8 minus 4. That's going to be 0. So your x bar is going to be your my over m is just going to be 0 divided by whatever we said that first one up there was. It really doesn't matter. 32 rho over 3. 0 divided by 32 rho over 3 is going to be 0. There it is. So my x bar is 0 down here. My y bar comes from my mx that I just found, 256 over 15 divided by 32 rho over 3. So this is going to be, you know, the rows are going to cancel out. This is 256 over 15 times 3 over 32. This is row, this is row, and they will cancel. 3 over 15 is 1/5. 256 divided by 32, that's 8. That's going to be 8/5 there, which is the same thing as 1.6 exactly. So you can either write 8/5 here if you like fractions, or you can write 1.6 if you like decimals. Same thing. All right, I hope that was helpful to you in being able to do your homework and prepare for your test on this material. This type of problem here with the planar lamina, it's especially difficult to remember all those formulas, and when you do f of x plus g of x, and when you do f of x minus g of x, when you find the average values. So just do plenty of practice problems from that. You probably won't have many problems on the test, but it probably will be worth many points on the test to go ahead and do this type of a problem. That wraps up everything that I have for chapter 7. So I'll come back next time and start talking about chapter 8 with a review of antiderivatives and basic integral techniques from basic integration techniques in 8.1. That's just a refresher of lots of stuff that we learned in chapters 4 and 5. And then we'll pick up with some new material in 8.2, and I think we'll have a lot of fun together in chapter 8. I really like that material. So see you for the next video.